In this video, we're going to talk about concavity and introduce the second derivative test. A graph is concave up on an open interval if all tangent lines to the curve in that interval are below the curve. And a graph is concave down on an open interval if all tangent lines to the curve in that interval are above the curve. So you could think of concave up being like an upward facing U, whereas concave down is a downward facing U. Any point where my graph changes concavity, so I go from either up to down or down to up, is called a point of inflection. So let's graph y equals x cubed minus 4x. And here I'm just using a 5 by 5 window. If I move from left to right on my curve, I'm going to see the concavity and also a point of inflection. So I notice when I draw my first several tangent lines, these tangent lines are above the curve. So that means where I am at in my graph right now, my graph is concave down. And again, we can visually see it looks like a downward facing U. Sometimes the graphs aren't as obvious to see whether it's concave up or down. So knowing the way the tangent lines are moving is very helpful in determining the concavity of a graph. I notice here that I change concavity. I go from concave up, where my tangent line is above the curve, to concave up, where my tangent line is now below the curve. So this point right here, x equals 0, is a point of inflection because I changed from being above to now being below. So we can see when we are concave down, the slopes of our tangent lines are starting to decrease. Right? We had a very steep slope, not so steep, and now it's negative. When we are concave up, the opposite is happening. So we have a small slope, so here it's negative, and then it turns to being a positive slope, and then a larger positive slope. So we are concave down on the interval negative infinity to 0, and we're concave up from 0 to infinity, with an inflection point at x equals 0. Remember that the first derivative test is going to determine the intervals where a graph is increasing or decreasing, as well as any extrema. The second derivative test that we're going to talk about in a little bit determines intervals of concavity as well as any inflection points, so where I'm changing concavity. Remember, extrema with the first derivative test is where I'm changing direction. Points of inflection are where I change concavity. In the first derivative test, we discussed that a function is increasing where its first derivative is positive and decreasing where its first derivative is negative. So a function is concave up if the slope of the tangent lines are increasing. So like we see here, here's our point of inflection. Our tangent lines are increasing where I'm concave up. That means that the first derivative is going to be greater than 0 if the slopes of those tangent lines are increasing. Well, in order to determine the intervals where this first derivative is positive, we need to take the derivative of that first derivative, which is the second derivative. So a function is concave up where the second derivative is greater than 0. So where the second derivative is positive, we're going to be concave up. A similar argument can be made for where we're concave down. A function is concave down when the second derivative is less than 0. So the second derivative test, if we're given a function, the function's concave up if the second derivative is positive, and concave down if the second derivative is negative. If f does have an inflection point, so if we do change concavity, then the second derivative is 0 or it's undefined.